More than 400,000 years ago, our ancestors first approached fire, realizing that it kept wild animals at bay. Through fascination and curiosity, prehistoric people came up with imaginative means to use fire for protection, heat, light, food preservation, and social gatherings. For most of human history, we have used multiple applications of fire to generate light and heat. But what brought us illumination at the flick of a switch? It certainly wasn't the development of candles. Since the 1600s, scientists and inventors have worked to understand the principles of electricity, making it possible to use it in our everyday life. Today's world, dominated as it is by faster and faster pace of new technologies, is the result of a revolution in physics which started at the end of the 19th century. Maxwell's laws of electrodynamics led to electricity, radios, and television. Thomson's Nobel-winning discovery of the electron led to modern atomic physics and set the stage for the development of quantum mechanics, opening up the era of electronics. New scientific theories, concepts, and discoveries proliferated and brought about cataclysmic transformations of the world at all levels: technological, social, and cultural. Created in 1954 by some of the protagonists of the 20th century physics revolution, CERN carries today the torch of the virtual circle of knowledge and innovation at an accelerated pace. As distant as it might seem from our daily lives, particle physics has always been a trailblazer for disruptive technologies which have benefited society at large. The invention of the World Wide Web, which was the result of the laboratory's unique collaborative environment, is one of the striking examples. The unprecedented scale and technical requirements of the accelerators, detectors, and computing infrastructure needed by particle physicists for their research has constantly pushed the boundaries of technology. The cutting-edge technologies necessary to build particle accelerators have found applications that go well beyond scientific research. Today, there are over 40,000 accelerators around the world. Only 3% of them are used for fundamental research. The rest are in industry or in hospitals to treat patients. The gigantic detectors built by physicists to explore the unknown have fueled new developments in many fields. From medical imaging to security, to art authentication and restoration, all the way to space exploration. To cope with the huge amount of data generated by the collisions in the detectors, scientists are constantly pushing the limits of computing technology, such as the grid, a system to share computer power and data storage across computing centers around the world, AI, and quantum computing. The new theories, concepts, and discoveries emerging from current and future research in particle physics will forever feed the virtual circle of knowledge and innovation. This interconnected journey will continue to unfold and is far from over.
Good evening and a very warm welcome to you all, both on the remote audience on YouTube and here present at the Science Gateway at this third event, which is part of a series especially organized on a very special year for CERN, our 70th anniversary. As you have seen from this movie, the focus of tonight's event is on a very important aspect of curiosity-driven research that is often forgotten in our utilitarian society. It's the very profound link that exists between knowledge and innovation. Here at CERN, in our quest to understand nature at the very fundamental level of particles, we push the limit of technologies in three main areas: particle accelerators, particle detectors, and computing. And thanks to a fabulous array that we have tonight with us of CERN researchers, industry experts, and elite scientists, including a Nobel laureate, who will take you through a voyage of discovery through these incredible machines and their surprising applications that are transferred from the laboratory to society. Let's get started with what's the bread and butter of this place, particle accelerators.
At CERN, beams of particles are accelerated to almost the speed of light inside the LHC, along 27 kilometers of superconducting magnets buried 100 meters below ground. There, two beams of particles travel in opposite directions, in separate beam pipes kept at ultra-high vacuum, guided by intense magnetic fields. Among the LHC's most celebrated accomplishments is the discovery of the Higgs boson, which explained fundamental aspects of our universe. The high doses of radiation used to destroy cancer cells are often delivered by the same technology that accelerates particles. Besides X-rays, protons, electrons, and ions of carbon and helium are also used in many hospitals to directly target tumors, reducing the damage to healthy tissues. Facilities at CERN, such as Isolde, Medicis, and Enthoff, produce innovative radioisotopes for advanced medical treatment and imaging. Accelerators have spurred advancements in artificial intelligence that are revolutionizing healthcare. Algorithms used to detect anomalies in the welding of the LHC have been adapted to spot human brain pathologies. CERN's unique expertise in superconductors and electromagnets is being applied to the development of more efficient energy transmission to accelerate the transition to renewable energy in the airplane industries. Of the 42,000 existing accelerators worldwide, 64% are in industry, 33% are in hospitals, and only 3% are used for fundamental research. Accelerators are not just tools for discovery, but beacons of hope for a brighter, healthier future.
And our first speaker will take us into the Large Hadron Collider and the entire accelerator complex of CERN is Alessandra Lombardi, a senior accelerator physicist at CERN. Welcome, Alessandra. Alessandra is an expert in linear accelerators, in particular the brand new LINAC 4, where the protons start their voyage into the accelerator complex. The floor is yours. We will follow Alessandra with two more speakers on a dialogue more focused on the applications. But let's first try to explain what are particle accelerators.
Okay, thank you very much, Paola, for the very nice introduction. And yeah, I've got a bit of a challenging task here to explain what particle accelerators are. As the title says, we are going to probe into the infinitely small. And to do that, I invite you to consider the smallest thing that we have at hand on our body. It's our hair. If we look at our hair, we have it has a scale of about 100 micrometers. But come with me in a voyage where we go into smaller and smaller volume, and we zoom in, starting from our hair, we will see cell at 10 micrometer scale. And then we will see that there is more and more structure to it as we zoom in and we make our field even smaller and smaller. We arrive at keratin, this protein, 2 nanometer in dimension. And then let's continue on. We arrive at atoms, carbon, oxygen, nitrogen, you name it. Let's follow the carbon, though, this time, and zoom in more and more with our magic magnifying glass. We will notice the structure of the electron orbitals. And then, if we are more patient and we keep on zooming in, and we zoom in and we zoom in, we arrive to the nucleus that is coming up shortly, just to give you an idea how really small it is compared to everything else. The nucleus of carbon is composed of protons and neutrons. And let's not stop here yet. Let's go even farther. We will see that the proton is actually a structure and is composed of 3 quarks, 2 up quarks and 1 down quarks for what matters. Now we have arrived to the scale that is 10 to the minus 15 meter. I invite you to think a moment about how small is this number. And this is the scale where particle physics today takes place. Okay, how do we go to that scale? Let's take this sketch that we have here. And let's start on the right-hand side. So if we have to distinguish or to study a bug, our eye is enough. Instead, if we want to look at one of those critters like acarian and so on, we need to take a magnifying glass. And if we want to go even farther and look at the tissues or cells, we need to have microscope or electronic microscope. Now, how do we go about to go and look at the scale of 10 to the minus 15? As you see in the sketch, we need to go to high energy accelerators. And whereas the first 4 things that I have described to you are probably familiar or somehow make sense, I really need to tell you why we need high energy accelerator to look into the infinitely small. Let's look at the sketch on the, what is for you, left-hand side. Let's look at the sketch on the left-hand side. It tells us the relation between energy and wavelength, so energy and dimensions. And if we want to go to a scale of 10 to minus 15, you see from this graph that we need to go to energy of 10 to the 12 or tera electron volts. Okay, tera electron volts is a very big number, and we cannot just go there in one jump. So how do we go about bringing some particles to 10 to tera electron volt? So answer is the Large Hadron Collider. But we start slow from a bottle of hydrogen. We extract protons from a bottle of hydrogen, and we accelerate. They go zooming down the LINAC. Now, if we were to accelerate with the LINAC all the way to tera electron volt, we will literally run out of space. So we go about by going around and around in circular machine. First the PS booster, then the PS proton synchrotron, then the SPS, and finally the LHC. But you see, we need to do this in 4 steps because the particle, as they gain, initially they gain velocity, and then they gain mass. They become heavier and heavier. So it's more and more difficult to keep them on a circular trajectory, and we need stronger and stronger magnets. So now the animation has gone on, and you have seen that once we are at the LHC, once we are at the TeV energy, then we let this beam collide in 4 points along the collider, where the 4 detectors are located. You will hear about detectors later. Now, I hope I have convinced you that the 2 most challenging elements and key technology in accelerating, whether in LINAC or in a circular machine, are radio frequency cavity to give energy to the beam fast and efficiently, and for what concerns circular machine, magnets that have become more and more powerful as the energy of the beam increases. I will not talk about magnets because there is Amalia behind me to do that. But I will bring you to the newest of CERN accelerator, the youngest of CERN accelerator, that's LINAC 4. As we said in the sketch, in LINAC we start with the hydrogen bottle, the source where we create the particles, and we give them energy. We call them slow particles as they come out of the source. They are only 1% of the speed of light, and we bring them to 50% of the speed of light at the end of the tunnel. Before I was saying it would be, we would really run out of space if we had to continue with the LINAC. And this is actually true, because in the LINAC, we give about 2.5 MeV of energy every meter of LINAC. So if we had to arrive to the T tera electron volt, we would have a LINAC as long that would arrive all the way to the pyramid. And certainly we don't want to do that. We want to stay on the CERN side. Okay, now we took 4 standstill picture of the LINAC that are exemplary to show you a bit the zoo of RF structure that is around, and also their complexity. So radio frequency quadrupole, drift tube Linax, L-coupled DTL, pi-mode structure, these are a bit exotic names, but behind this structure there are years of R&D. For example, in the case of Linac 4, it was some 5 to 10 years of R&D to achieve structure suitable, efficient, and that can work 24 hours 7. Just to give you an idea what I mean with this, let's take the first of the structure, the radio frequency quadrupole, and see and take 3 snapshots in the 90s, 2007, when Linac 4 RFQ was designed, and the new RFQ high frequency. So we went from a structure that is bulky, heavy, that doesn't have very efficient acceleration, so half a MeV per meter. We went to a structure that is 9 times lighter and much more efficient in the acceleration. And this step was necessary to be able to transfer this R&D to societal application. So one can ask, what use do we do of this stuff in society? Well, there are several applications of what we call low energy accelerator. Low energy is always referred to the LHC when you are at CERN. Environment, aerospace, healthcare, as you've seen in the trailer, digital and quantum. And I would like, in the time remaining together tonight, illustrate you 2 applications. The one for healthcare and the one for art diagnostic, very new and very interesting. Okay, so you have seen that treating cancer with the particle is something that is already done in hospital. But what is the next challenge for us accelerator designer is to be able to accelerate carbon ion, not proton, in a linear accelerator, in order to be able to have highly efficient acceleration, fast energy variation, and still remain in a footprint 30 by 15 meter that is reasonable for a hospital. What you see on the right-hand side is a nice picture of the very first step of this challenge. Now, I talked about another application that I was going to discuss with you tonight, is the one of art diagnostic. So using protons at the energy of about 2 MeV for art diagnostic has already been done. As a matter of fact, in the basement of the Louvre, for example, there is an accelerator. But this accelerator is enormous. It's almost as big, well, it's as big as half this auditorium. The idea is to make a transportable accelerator. And our path towards reducing the size and the complexity of accelerator goes exactly in this direction. We have a nice realization called the Machina project with the INFN in Florence. This accelerator will be turned on very, very soon, the next month. And if you want to see one of such accelerators, you actually don't have to travel to Florence, but you can go here to the Science Gateway, to the brand new visitor center, where there is actually a real accelerator, a real Linac. You can see it. You can see in this nice movie. It's only 1 meter in length, and will be open to the public, not just yet, but during this year. And the public will be able to learn about how an accelerator works and all in all its glory. The particle from this accelerator have an energy of 2 MeV, so super slow for CERN. But just to tell you, the scale here, super slow, those are still particles that would make the turn of the Earth around the equator in less than 2 seconds. So, okay, this is for super slow. I think this is all we had
Thank you,
tonight.
Alessandra. We have a lot of speakers, so we are going fast with the pace. You were perfect with timing.
Okay.
So ELISA is the only place at CERN where very soon you'll be able to see a beam with your own eyes,
exactly.
Which is not the case in other accelerators. Thanks a lot, Alessandra. We'll see if we have the option for questions later. Now, Alessandra mentioned a very important technology for accelerators, that is magnet technology. With the next speaker, we are going to dive into the world of superconductivity. Amalia Ballarino, a colleague from CERN, she's a nuclear engineer from Torino. She arrived at CERN to do her PhD thesis, and she stayed. And she's an important contributor to the superconducting technology of the LHC and now of the high luminosity LHC, the next stage. So Amalia, let's find out about superconductivity. Let's start with the simple. What is superconductivity?
Yes. We
need the slides.
We need the slides.
Elisa is beautiful, but yes, great.
Yeah. As we were saying before, accelerators has always been very important from the point of view of driving innovation. Fundamental physics is the driver, but innovation which comes from accelerators then very often also have impact on society. So we develop and we push to the limit technologies, and one of the technology which is essential for high energy accelerator is a superconductivity. So let's have a look of when superconductivity was discovered. Superconductivity was discovered in 1911 by Kamerlingh Onn, who is a Dutch physicist. It was the time of the Cold War, where physicists were trying to reproduce very low temperatures. And when we think about very low temperatures, in the case of Kamerlingh Onn, it was the temperature of the liquid helium, 4.2 Kelvin, which is minus about 268 degrees Celsius. After having succeeded in liquefied helium, he tried to measure the resistance of a wire of mercury. And he discovered, and as we can see on the plot, which is at your left, that the resistance of mercury was going down suddenly to zero at the temperature of the liquid helium. It was an important discovery, which was not predicted, as sometimes happened by theory. There were theories which were predicting resistance going down linearly with temperature, reaching asymptotic values, or even increasing exponentially because somehow electron could have been frozen at low temperature. So this was really a discovery, unexpected, and enabled by the liquefaction of liquid helium. Which is the main characteristics of superconductors? Well, superconductivity is a quantum mechanics phenomenon, but from the microscopic point of view, the main characteristics is that superconducting materials below a given temperature, which is called Tc, the critical temperature, do not show resistance. So resistance drops down to zero. If you measure the resistance as a function of temperature of the other metals, also good conductors like copper, you will see that the resistance goes down with the temperature, but never drop to zero. And which is the consequence of superconductivity? Is that you can transfer very high currents in very small cross-sections without dissipating power. So with superconducting material, we abolish the Ohm law. We pass current without power consumption, although we have to spend power to maintain the low temperature. We can transfer very high currents in small cross-sections, which means very high current density, and this is why the technology becomes enabling for magnets. Magnets need to generate very high magnetic fields, which means they need to transfer very high currents. If we try to make magnets with conventional metals like copper, we would be limited to magnetic fields of the order of 2 Tesla. When we use superconductors, for instance, niobium titanium, like in the case of the LAC, we can generate field as high as 8 Tesla because of the very high current that we can transfer.
It's really incredible to underline how a serendipitous discovery becomes a high-tech enabler.
Absolutely. Superconductivity is an enabling technology for accelerator.
Yes, so this is the LHC is the largest superconductor in the world. It's amazing, 27 kilometers of superconductivity. But why do we need it? You made the correlation with magnets, but let's spend another moment to understand why it's necessary for the LHC.
So the Large Hadron Collider is the largest accelerator ever built. It's the highest energy. To reach high energy, we need high fields, particle at collision. To get high energy, we need high fields, and to get high fields, we need high currents. What we can see in this plot, we can see the cross-section of a dipole magnet made from niobium titanium superconductor. Basically, what you can see inside are the two beam pipes, where we have the ultra-high vacuum, where the two particles are beam particles are circulating, counter-rotating, and around the beam particles we have these that you can see kind of orange color coils made from superconducting material. All inside, we have helium, which is maintained at a temperature of 1.9 Kelvin, superfluid helium, even lower than 4.2. The lowest is the temperature, the more the superconductor can transfer current. We have a complex mechanical structure around the coil, which enables the coils to maintain a very well fixed and defined position. And then we have another structure that we call cryostat, inside which we have a vacuum, a thermal vacuum, which enable to maintain the cold. So we have to think that in the Large Hadron Collider, we have a 1.9 Kelvin all around the 27 kilometers of circumference.
The coldest place in the world. It's
the coldest place in the world, indeed. Thinking about high currents and giving some number that we can bring home, a wire of niobium titanium of 1 millimeter is able to transfer at liquid helium temperature about 1,000 ampere. This is very high, but it's not sufficient because in the magnets we transfer current as high as 13,000 amps. So we connect many wires in parallel in order to make a cable, and we rely on cables made from niobium titanium wire that in the LAC magnets transfer current as high as 13,000 ampere at 1.9 Kelvin. These are gigantic magnets. We want to study the infinitely small, but we deal with very big structure. You will see later on the structure of the detectors. Here you see the magnets, which are the main components of the accelerator. Each dipole, we have seen the cross-section before, is about 15 meters long, and it has a weight of about 30 tons. We have exactly 1,232 dipole in the LAC underground, and then we have many other superconducting magnets, about 10,000 altogether, which enable us to steer and focus the beam along the 27 kilometers of circumference. Here you have also a very nice picture which shows when these 15 tons dipole were lowered down in the underground. We should remember that the LAC tunnel is about 100 meters underground, so all these structures, which were clearly constructed at the surface, had to be brought down in the tunnel.
Yeah, I'm sure some of us remember the traffic of the dipoles on trucks between the Meran site and
as a special transport.
Special transport for 2 years in a row, 24 hours a day, all descending from a single hole, the only one capable of taking 15-meter long objects.
So altogether, in the LAC, we have, as we were saying, about 10,000 superconducting magnets. We have to transfer a huge amount of current. The current is generated at room temperature by power converters, and we have to bring it down into the cold where the magnets are operated. And we have to transfer altogether 1.5 million of ampere. In the LAC, we have about 30 tons of superfluid helium at 1.9 Kelvin. We are very close to the zero absolute at minus about 271 degrees Celsius, and we use about 1,200 tons of niobium titanium cables. So this is a large application of superconductivity.
And you mentioned the very special features of this magic phenomenon of superconductivity. And of course, we will listen later to the next speaker about applications, a whole variety of applications to industry. But you're working yourself on a specific industrial application. Can you tell us just a quick word about it?
Yes. The real commercial industrial application of superconductivity is MRI, magnetic resonance imaging. In MRI, for doing the images, the detailed 3D images of our body, we use high-field magnets, which are really a spin-off of the work which was done starting from the late 60s in the accelerator technology. And in fact, the MRI industry consumes about 4,000 tons of niobium titanium per year. So the MRI industry maintains the market of superconductors. We were saying about transferring high currents in very small volume, and clearly one application of superconductivity is power transmission. Here you can see in this nice picture a recent application that we did at CERN, a power transmission line which is going to be used for the high luminosity upgrade of the LAC, which is able to transfer 120,000 ampere in DC mode at a temperature that we consider high. 50 Kelvin, still minus 223 degrees Celsius, but high, much higher with respect to 1.9 Kelvin of the magnets. So these are new materials, what we call high temperature superconducting materials, which have the potential of having many applications also for society.
One of them?
One of them is magnesium diboride that we have inside this line, and we also have REPCO, high temperature superconductor. Another application on which we are working, which is at the stage of being studied, is electrical transmission in aeroplanes. We were contacted by Airbus Up Next, who is looking at a future technology in the plane for future low emission planes. And we have developed, together with Airbus Up Next, a transmission line using superconducting material, where the great advantage here is that the line is very light and therefore appropriate for use on the plane. This project is in the context of an R&D activity which is done in this case by Airbus, which look at future electrical transmission in the plane associated with fuel cell, having nitrogen on board. Liquid nitrogen has a temperature of about 20 Kelvin and can therefore be used also as a cryogen for the cooling on superconductor, and also electric motors for the future of low-emission aeroplanes.
And this is one of the many collaborations with industry that are carried out by our knowledge transfer department at CERN, together with, obviously, with the researchers. So on this, I think this is the perfect point to say bye to you, Amalia, and of course, many thanks, because the next speaker will take over exactly from the industry, from the aeronautical industry. So I'm very pleased to welcome on stage Tabea Arndt. Tabea is a professor at the Karlsruhe Institute of Technology, KIT, member of the board of directors at the Institute of Technical Physics in Germany. Tabea, you're a physicist, a superconductor expert, but what strikes me most in your CV, many titles, is that you are the curator for the German Ministry of Economy and Climate Research for high temperature superconductivity in high energy efficiency industry. So this says a lot to what Amalia just hinted at, that this is a potentially disruptive technology, especially nowadays where we need a more sustainable industry.
Thank you for this kind introduction. I'm happy to be here to tell a little bit about the power applications, and I'm extremely happy that Amalia provided a nice handover to me with this electric aircraft, because fossil-driven electric aircrafts have the challenge to have heavy fuel and lightweight propulsion devices, the turbines. And this approach Amalia mentioned is exactly the opposite of that, a paradigm shift. It's really having lightweight fuel, the hydrogen, and now a heavy electric drivetrain. And high temperature superconductivity might help to lighten this drivetrain. And this is exactly what we would like to have in power applications. We are not so much relying on low temperature superconductors. The superconductor has to pay for its value, has to pay back for that. And so we are looking for high temperature superconductors. Here's an example of Amalia's HTS compound conductor, which may be used in power applications too. And, but what we have not only these overlap in materials, but an overlap in challenges in this technology. One of these challenges is we always have to get the current from high temperature levels to low temperature levels, to the inner part of the superconducting application. And that's by the means of so-called current leads. And what you see in the middle of this slide is a current lead for LHC. This was built some decades ago already, but what you see on the right part of the slide is, let's say, the other extreme of power applications. This is fusion technology. So this was a current lead for W7X, the fusion reactor in Germany, which was built by our institute. And this is not only important for magnets and for aircrafts and for other applications, but you see the importance of these current leads in this, let's say, heat load pie. So the biggest loss of cold is coming via the current leads. Usually in this example for rotating machines, you see the yellow segment of the circle is really the biggest one. So it's important to work on this technology brick current lead. We are leaving this field of base technology, and I would like to go into the field of
power engineering.
Power engineering, and especially electric grids.
Yes.
And what we see here is not superconducting. I have to emphasize that. This would never happen with superconducting equipment. This is a conventional substation burning with control. The control mechanisms have been burned too. And what happens is that the overhead line is heating up a lot. You will see that in the course of this video, and I will talk a little bit further in that. The overhead line is getting really hot, smoking, and finally touching ground and destroying even other equipment then. And
so if they had a superconductor, this wouldn't happen.
Exactly. That's exactly the point. And what I can show in the next slide, I will slightly wait until you see the smoke on the line. You see that now. And this goes for some further seconds, but we want to go further in this presentation. So what can really help is the use of so-called fault current limiters. This uses the switching property of superconductors. At a certain overcurrent, they switch into normal resistivity. You see that in the middle part of this slide. And on the left side, you see how such a device would look like in a small power grid, and at the right one for a high voltage power grid. So this is really helpful, and this could avoid even the remote fault currents when a substation would totally be destroyed.
Then we have a very surprising application that you showed me in a different energy field.
Yes.
In the field of renewable energies.
Yes, for now we have been touching the field of power transmission, but for generation, this is superconductivity, high temperature superconductivity might contribute too, especially in the case of wind power turbines. There have been already some installations and there are ongoing projects, and the special aspect using high temperature superconductors is that you can replace several tons of rare earth permanent magnets by 50 grams of rare earth material within the superconductor. It's not only energy efficient, it's more performance, and it's material efficient. That's really a threefold benefit.
So superconductors are going to make wind power even more green.
Yes, and more useful and more powerful and so on. A lot of benefits, I can tell you a lot of technical details, but not for this evening, I think.
We can now move to another sector even.
Yeah, it's not only the electric power grid which is benefiting in sustainability aspects from high temperature superconductors, but it's, in this case, I show you an example of an industrial magnet. In this case is a DC magnet, so quite similar to what we have seen before in Amalia's talk, for example. But in this case, it's a DC magnetic field with a rotating metallic billet for metal production. And the clue is that you can save about 60% of energy, and you can avoid gas-fueled furnaces to reduce the CO2 emission on this production. So this is really increasing sustainability in industrial processes.
I know you have many more examples, so let's go quickly through some of the most striking ones, at least for us in our everyday life.
Exactly. So it's not just rocket science or hidden technology. For example, there have been works on transformers for trains in the past to make this lighter and more compact and more efficient. This is one of the main levers there. Or if we go a little bit far away, this has already been built. The dark blue machine is a 4 megawatt ship propulsion electric machine, a motor, and you see a liquid hydrogen vessel which is planned for the near future. Or really going to your neighborhood, electric trucks, fuel cell electric driven trucks. In this case, it's still a conventional one, but this is driven by, as a fuel by liquid hydrogen. And it was a record travel of more than 1,000 kilometers with one refilling. And we are working in a project to improve the electric motors by superconductivity, by high temperature superconductivity, to further improve the efficiency of these things.
And there's some futuristic applications as
yeah,
well.
Futuristic, but on the other hand, really on our agenda, on the Japanese agenda in this case. This is a high-speed maglev train. This is based on the niob titanium technology and even using persistent mode special features of superconductivity to reach high-speed transportation for the public in 2027.
Not as fast as the LHC though.
No, this is much more mass in there, so not as fast. But now I would like to close this circle of innovation because I'm not here only for this evening. I went to this to CERN this time for participating in the ship planning for the experiment on the muon collider activities. And this is a special experiment, and we now transferred or proposed a cooling concept which came out of the power applications for a special magnet you see in the bottom right of this picture. So now we have a chance to really close the circle and bring back technology bricks from power applications into magnet technology, and we are looking forward to make this new technology available.
Thank you, Tabea, for this perfect illustration of the virtuous circle of knowledge and innovation from particle physics to technology and back. So we now close the session on accelerators. We just said that CERN's bread and butter are accelerators, but accelerators without detectors at CERN are pretty useless. We need detectors to detect the particles emerging from the collisions. So we launched this session with 3 more speakers, and we start with a short clip.
The particle beams inside the LHC collide at 4 locations around the accelerator in 4 large particle detectors, ATLAS, CMS, ALICE, and LHCb, built by collaborations of physicists and engineers from across the globe. It is in the center of these gigantic instruments that collisions occur, and where new, previously unknown particles and interactions may be identified. Particle detectors allow us to look at the universe at its smallest scales. The technologies and materials developed by physicists to build and operate these instruments have fueled new developments in many fields, from security scans in airports and borders, through medical imaging, to assessing the hazards of radiation in outer space. Positron emission tomography is a medical imaging technique that works by detecting photons emitted from positron annihilation. Scintillating crystals used in the LHC experiments to measure particle energies are now being used to advance this technique. The Metapix readout chip was developed at CERN to track single particles at the center of the LHC detectors. It works like a camera, detecting and counting each individual particle hitting the pixels. This novel technology has found a vital role in medicine. Its color X-ray imaging technique produces clearer pictures that will help doctors give their patients more accurate diagnosis by differentiating tissues with similar densities but different compositions. The extremely high resolution offered by the Metapix chips, coupled with their non-destructive spectral imaging, also provides a unique tool for authenticating and preserving cultural heritage. In the harsh environment of outer space, unique challenges arise, especially in monitoring cosmic radiation. CERN's TimePix device, developed for the challenging radiation environment of the LHC, now serves as a vital component aboard the International Space Station and NASA's Orion vehicle. This technology is capable of measuring complex radiation fields and their impact on electronics, thus safeguarding astronauts from the unseen dangers of space radiation. These are just a few of the applications of CERN's fruitful collaborations with industrial and research partners in the field of detector development.
And let's open now this session on particle detectors, sensing the invisible, with Daniela Bortoletto, who is head of particle physics at Oxford University. She's very well known at CERN because she's a member of the ATLAS collaboration, 100 meters below our feet, right here. And Daniela had a key role in developing part of the ATLAS detector, in particular the silicon detector upgrade. And we couldn't choose a better person to give us an introduction on what are these detectors and how they work. The floor is yours, Daniela.
Good evening. Tonight I would like, thank you. Tonight I would like to take you with me and guide you through the fascinating world of detectors in our experiment here at CERN. You've seen this picture already, so going around the ring, you know already that the beam division is going to collide the beams in the center of our detectors. And we have 4 big detectors here at LHC. The first one, Atlas, which is down here, is the biggest detector ever built. It has a length of 44 meters and a diameter of 25 meters. It's almost half of the size of Notre Dame Cathedral in Paris. So really an awe-inspiring detector. And it can measure particles with the precision of better than a human hair. Okay? And it was built and optimized to study the Higgs boson and to find particles beyond the standard model. Another big detector, a general detector, is CMS. And CMS also helped for the discovery of the Higgs boson in 2012. And CMS stands for Compact Muon Spectrometer, but it's not that compact. It's still like 15 meters in diameter, so it's pretty big, and it weighs almost like 30 jets, jumbo jets. So it's really quite heavy also. Then we have ALICE, which is an experiment that is really built to study the quark-gluon plasma, an element of matter that was existing very close to the Big Bang. And it's really by studying the quark-gluon plasma, we can get information about the nuclear phenomena that happens in astrophysical objects and, for example, in neutron stars. And then there is LHCb, which is a detector that studies matter-antimatter asymmetry using big quarks. And this is phenomenal because, after the Big Bang, we saw that there was the same amount of matter and antimatter. But now you know that we are here, there is a lot of matter and no antimatter. So it's pretty cool. I would like to take you through some pictures of this amazing detector, which are like electronic cathedral. Here is a picture of Atlas, and you can see something that resembles a wheel. This is a muon chamber, and we call it the big wheel because it's really big, as I told you. Here is a picture of CMS. You can see again the muon detector, again very big, and also some part of the calorimeter that are measuring the energy of the particles. Here is a picture of ALICE, where you see a detector which is called transition radiation detector. And this detector helps you distinguish pions from electrons. And you can also see in an image all the cables coming out of the detectors. A ton of cables. And this is really a major issue, actually, with our detectors. And then here is a picture of LHCb. It's focused actually on the beam pipe. This is like 19 centimeter long, so it's really the longest beam pipe, 19 meter long is the longest beam pipe of the LHC detectors. And it has been built, the material, the shape, have been built to be as transparent as possible to the particle of produced by the beam. And this is an example of how the detector has really to be intimately connected to the, to the machine. You can see also, for example, the spider web that is holding the beam pipe in this picture. I think that somebody showed you already the remarkable scales that we deal with. We have these huge detectors, that are really like cathedral, I told you. And then we are looking at elementary particle. And what we mean by elementary particle is really a subatomic particle which is not composed by any other particles. And you can see here in the picture, you can see the size of an atom. And an atom is like a billionth of a meter, so it's very small, and still is made up of a nucleus, which is 1,000 times smaller than the atom, and the nucleus is made up of protons that are 10 times smaller than a nucleus, and then the elementary particles that we are trying to study are even 1,000 times smaller than the proton. And again, this is as far as we know. By going higher in energy, we can probe smaller and smaller distances. So, but because these particles are created, are very tiny and are traveling very fast, we need to study them with quantum field theory. And this is a very important theory because it really explains why an electron here in Geneva is the same as an electron in Oxford. But because when we are doing a measurement, we are perturbing this quantum field, and as you can see in this sketch here. And by perturbing it, we are also disturbing this field, as is illustrated here. We are collapsing the field, as we say. So how do we see particles? Well, our detectors, we call them detectors, but they're actually an ensemble of sub-detectors. It's almost like, I don't know if you want to call it a Russian doll, with each layers of the doll that you are opening, doing something to the particle, trying to understand which particle and understanding the particle better. So here you see a picture, and again, a lot of our particles actually are not stable, but the ones that we see often in the detector are the ones that are stable. And you can see that different particles will give a different signature in each of the detector. And by putting together these imprints, we are able to distinguish particles. I just do you an example because it will take you too long to go into the details. But for example, here you can see an electron in this track here, and you can see that the electron will be stopped by the electromagnetic calorimeter, and this will be a sign that you have seen an electron. And in the muon chamber, for example, you will see only muons. But what are the interactions that allow us to see this particle? Well, it's really the electromagnetic interaction, which we are very familiar with. And when an incoming particle goes through a material in a detector, which is chosen appropriately, it will, for example, it will ionize the detector in the material. For example, in silicon, this will cause the production of electron-hole pairs. In a gas, it will create an ion and an electron. And then you can collect this charge, and you can have a current that will tell you that the particle went through this part of the detector. Again, there are other interactions that can happen, like, for example, the incoming particle can interact, for example, with the nucleus and can be bent by the nucleus and emitting a Bremsstrahlung electron, or otherwise as a Bremsstrahlung photon. And another mechanism is, for example, if the particle is traveling faster than the speed of light in that medium, again, there is an emission of Cherenkov radiation, of photons, that are detected, that are going in the same direction of the particle in a cone. And when the particle crosses the boundary through different material, it can also emit transition radiation. So all of this kind of interaction of a particle with a material can be used to detect a particle. I would like now to give you a few examples of detectors that have really revolutionized the ways that we are doing physics. One of them is a multi-wire proportional chamber. I will call it wire chambers, which was developed in 1968 at the end of the 60s by George Charpak, who received the Nobel Prize. And before this invention, what we will do, we will take picture in a bubble chamber, but this really limited the rate of the events that we could study. Again, what Charpak did, it put a lot of wires, as you can see in the picture on the right-hand side, in a gas enclosure, and each of these wires could be read out by an amplifier. And they were also at a certain electrical field in this gas. And so, for example, when a particle will go through the gas, it will create, as I told you already, an ion and an electron. The electron will be attracted by the wire, and while it will be attracted, it will gain energy and in this electrical field, and will create more electron-ion pairs that will be collected by the electronic and amplified and passed to a computer. And this fact really allows us to increase the rate of our experiment by a factor of 1,000, really a large factor. Charpak got the Nobel Prize because these wire chambers were used, for example, later on for the discovery of the W and Z boson, the quanta of the weak interaction, and also they were employed for a lot of biomedical application. He actually founded a lot of companies, part of this, this circle of knowledge and innovation, and he was especially interested in applying the particle detectors that we develop in particle physics to try to decrease the time and the dose in human radiology and improve actually the imaging. And he formed several companies. He was actually a survivor of the Dachau concentration camp, and he was really committed to humanity. Another great revolution was the silicon revolution, which happened at the end of the 70s, in the 80s. It was really allowed by the fact that there was a big development in the microelectronic industry that led to a big miniaturization of electronics. And again, by silicon, that allowed, for example, we knew at that time that there were particles that will be very short-lived. These are particles, for example, that contain the charm quark. And this particle can decay in about 1 picosecond, so a millionth of a second, a very short time. But because these particles, again, are boosted because they are, they're traveling very, very fast. You have what is called the relativistic boost, and so they can travel a little bit before decaying. So if your detector is precisely enough, you can see this decay. And that's what was done, for example, in the experiment on the right, which measures the lifetime of charm, tau, and bees. And as you can see, it was a tiny detector. You can see the sunglasses nearby, to give you an example of the size. And you can see here again one of the pioneers on the left is Kemmer. And he was, for example, again, somebody who went to found a company, K-Tech, which is working now in silicon photomultiplier. So here to give you a little bit of an idea of what we do with the silicon detector. For example, one of the things that we do, we put them in layers in a detector, and then when the charged particle will go through this layer, it's usually in a magnetic field, and so it will bend, and we will really track the radius of curvature of the particle. And by measuring the radius of curvature, because we know the magnetic field, we can measure the momentum of the particle. Also, as I told you, we can find this lifetime of the particles, this decay length. This is illustrated on the side of the screen. So you can see here that, for example, a particle here, you have a lambda sub c, a particle that contains a charm quark, an up quark, and a down quark. And it has a proper lifetime of 60 micron, but again, it can be boosted, and so it can travel a little bit, but it doesn't not reach our detector. It decays before reaching our detector, but because the silicon is so precise, we can infer back, we can track back the particles. We can see that they are coming from a decay point, which we call the decay point, and then we can measure the distance between the decay points and the interaction point of the proton, and by that we can measure the lifetime of the particle. So really, silicon has employed amazing things. I want to show you some picture of some beautiful silicon detectors. You can see on the top a silicon strip detector, which was built for Atlas. You can see the size because there is a technician sort of behind the silicon detector. And this was assembled actually in Oxford, okay? And then you can see the CMS detector, on a strip detector. You can see some of these layers that you told you before to measure the momentum. And underneath, you can see a picture of the LHCb detector. This is a detector that gets closer to the beam pipe. It actually goes to the beam. It just actually goes inside the beam vacuum, and it goes to 3 millimeters from the beam. And on the last detector is a very innovative detector. It's the ALICE inner tracking system, ITS, and this detector is using monolithic pixels. So you are using actually the silicon in the chip itself to detect the particles. And this is something that will become more and more used in future detector. And this system has 12.5 billion pixels. Okay, so this is really an amazing. These silicon detectors have enabled amazing discovery. One of them is in 1995, is the discovery of the top quark. The top quark decays into big quark. And in this picture, if you were able to look at the picture a little bit better, you will see two jets of particles that contain tracks that are not coming from the primary vertex, but they're coming from this decay vertex from the big quark. Similarly, for the other picture that is from Atlas, from the decay of the Higgs to two big quarks. And in this case, the Higgs was discovered in 2012, but this decay was only discovered in 2018. And this is really an important decay mode of the Higgs particle because it's the largest one. And so it's the one that will allow us to study the Higgs better and, for example, to understand if the Higgs field will give mass to the Higgs itself and to study the Higgs potential. So this is pretty cool. So we are going from particle physics to technology and back. And again, I think that you saw it mentioned a couple of times, there is a TimePix MEDIPix chip. This is really a revolutionary chip that has been very, very important, not only for particle physics, but for medical physics. It was developed by the MEDIPix collaboration, and we have actually the chair of this collaboration here, so I have to be careful about what I'm saying, probably. So, and this chip was really designed for imaging and detection. It is equipped by a pixel that can count per pixel the charge that it traverses pixel, and is really optimized to yield high resolution, high contrast, and noise-free images. It is not a monolithic detector, it's part of the hybrid detector, and so it can be optimized, for example, for particle physics to use with a silicon detector, or for medical imaging by using a different material, which is more sensitive to photon used in medical physics, like, for example, cadmium telluride. And again, I think that this is a fantastic example of from particle physics to technology and back. This chip is, for example, using the LHCb pixel detector, but is used a lot in medical imaging.
Thank you very much, Daniela. Thank you very much, Daniela, for this instant course into particle detection. Very lively, very much in depth. We are now, thank you also for giving me the bridge to the next speakers, because TimePix chip is actually the subject of the next two speakers. We can start with Jan Jakubek, who is a nuclear physicist by training, but he also passed by CERN, obviously, in his early career. Then he went back to your country, to Prague, in the Czech Republic, to create Advacam, a highly innovative company where detector technologies are applied to a variety of fields. Jan, so everything started from this object that Daniela described in the previous slide. You created a company based on this.
Yes, that's true. Actually, I was part of this wonderful MEDIPIX collaboration for many years, and we were developing this little brother of these large detectors used in high-energy physics. But we had an idea that these detectors could be used also out of physics, that we can use them for imaging. Basically, the principle is that here in CERN, we study particles, but once the particles are understood, we can use those particles and let them pass through some object, and recording them afterwards, we can conclude what is the structure of the object, so we can make images which are better than before. So let's see some examples. I brought with me a few of those like miniature detectors. We do different sizes of these detectors for different applications.
So this is a detector. It's not a USB key, huh? It's a detector.
It looks like USB key, but you cannot store there anything. It detects particles. It's basically a small camera, and actually it shows you radiation which actually falls in it. And since those detectors were developed to recognize different types of particles, we can not only see them, but we also can recognize what are they. And I will show you first. Okay, that's the picture we see actually, which is recorded by this detector lying here.
So basically, this is the particles that are all around us.
Yes.
In this room in the Science Gateway right now.
It's
a live recording.
Exactly.
Live imaging.
Yes, I will start it
of
over.
the invisible particles that surround us all.
From zero. And meanwhile, actually, what we see, not only there. Actually, I hope that I would see also the slide, but doesn't matter. We will wait until some particle would come. I brought with me some piece of glass. This is like decorative glass you can buy in some shops. And it contains like small amount of mineral which has a natural radioactivity. So it is not considered to be radioactive. It is just
everything is radioactive.
Everything is radioactive, including me and you. So and we immediately started to see what happens. So there are like traces of particles coming through the sensor, and they have different shapes. So some of them are curving, these are electrons. Some of them are just like dots, these are photons. So there could be gamma photons, there could be X-rays. And if you would be lucky, we can see maybe some alpha particle from radon decay in the room. If not, then I brought another piece.
More powerful, more radioactive?
No, it's actually part of the smoke detector. Yeah? So this is used in smoke detectors, which are normally over your head, actually to send warnings if some fire would happen. And we see the alpha particles actually from this sample. So then I would ask to
Thank you for this little experiment. We needed a little bit of break after the very intense
if you can
presentation of Daniela.
Yes, switch back to these slides. So actually, what we have seen are such images like this one. Actually, this one was recorded in my office in Prague, and we see there, except of those alpha particles, these big snowflakes, we see like strikes of muons, which are exactly the same muons which are recorded actually by Atlas detector here. But of course, those muons, they are not created only during such experiments. They are naturally present.
They come from the cosmos.
They come from space, actually, to us. So if I would continue to other applications, those properties, they can be used for imaging in industry. That's exactly what we do. For example, for a new aircrafts built now using composite materials, you need some methods which would evaluate the quality, whether the material would withstand extreme load during the flight. And for that, the novel imaging methods are needed. So that's exactly what we do, for example, with Boeing. Then actually we have a few other application fields which are very nice. One of them is mineral inspection for mining industries. We are able to basically show content of some valuable materials within the rock, within the stone, and then we can say to mining company which rock to be taken and further processed and which should be excluded, which saves a huge amount of energy and toxic waste.
Non-invasive mining, essentially.
Exactly. And then there are applications actually in biology, in space, and one of very nice applications which I like very much is application in education, which should be shown here. We are all studying, and our kids are studying physics in secondary schools, but everything we learn about radioactivity and radiation, we just read in textbooks. So we cannot actually see these things. And having such a detector in front of you, it allows you to play. So you can put there these pieces of different materials like granite and check what comes out. You can take it to your cellar and see the
You can do
there.
little experiments like we did just now.
Exactly. So this is used like that. And I have one very interesting or nice example of some experiments we can do with students. This was done during the COVID crisis, where people were discussing about masks, whether they would help or not. And there is a very nice thing with masks. So I used the fresh mask, which is actually shown back. Over there, and I placed that over the detector, and I didn't see much. Then I used that mask for 5 minutes of breathing, and put the mask back on the detector, and I immediately started to see particles coming out of that mask. Why is that? Yeah, because actually since some decay products of the radon in the air, they stick to aerosols and dust particles, they are filtered out by the mask, and then they are seen. And the very last image shows what happens when I use that mask only for exhaling. So I was inhaling through the nose and exhaling through the mask, and I placed the mask back to the detector, and there was nothing.
But you got it all in your lungs.
Because I filtered it out in my lungs, which is normal. We do it always, every day. So these are such examples.
Yep. These are fun examples, very good for education. Let's go to the more serious stuff.
And then actually, since we can recognize those particles, of course, we can bring the detector to some environments which are different from Earth, for example, to space. Here, actually, on Earth, we have advantage because we are shielded by atmosphere and magnetic field, so we are not directly hit by space radiation, which is shown nicely here. So we are living within this kind of protective cover. So the most of the particles coming to us from sun and from galaxies, they are passing us. But if we send there some electronics or some people, astronauts, who are supposed to work there, we have to actually protect them against the radiation. And moreover, if we would send them farther away out of this magnetic shield, for example, to moon, then they would be hit directly by this space radiation, which can suddenly increase by really 5 orders of magnitude, and it would be really
So you can
difficult.
predict space weather,
yes,
essentially.
Yes, we can predict the space weather.
From space to another sector, we are running out of time a little bit, so let's go fast through your last 2 examples, which are really fun.
That's very last one, because such a small detector can be mounted to a drone, for example, and it can search for some sources of radioactivity in environment to send some warnings if there will be some potential threat, like it is.
Also on robots?
Yes, then actually it could be detected.
Thank you very much, Jan, for this nice tour of fun applications to education, space, weather, radiation with drones. It's now time to call on stage our next and last guest of the detector session. So Dr. Stefan Kappler is Vice President of Technology and Innovation at Siemens Healthineers. He's a physicist by training as well, was a doctoral student at CERN, visiting researcher at Fermilab in the USA before joining Siemens in 2007. And you were awarded Inventor of the Year 2015 at Siemens for your achievement in photon counting, computed tomography, photon counting CT. This is something Daniela anticipated a bit, so she introduced us to these specific detector techniques coming from particle physics. So, Stefan, you were among the first participants in a workshop organized at CERN since 2011, and is still organized nowadays, that puts together the medical community with the particle physics community. So it's really at the intersection between academia, research, and the medical industry. And you immediately believed in this kind of meetings. At the time, it was not so usual, although physics and medicine go hand in hand since the times of Röntgen, but this was really a workshop to work together. Why did you believe, why were you so convinced in especially this technique?
Yeah, the technique, of course, I was convinced of because of my experience, but most of all because of the scientific community behind. And I'm really convinced about what you can read here. I do believe that scientific community is CERN like an institution, And conferences like the spectral imaging workshop we're having every 2 years here at CERN, they are fundamentals of detector innovation in medical imaging.
So what is the novelty of this photon counting technology that you are specializing in? What are the advantages for medical imaging?
Let's take maybe a look, yeah. So when we do X-ray imaging in medical imaging, we send X-rays through the human body and we measure the X-rays after the patient or after the body. So typically, and this is an example from computer tomography, the X-rays arrive at the detector, they convert into visible light, and then we collect the visible light with photodiodes, and the amount of light just gives us information about the body. With this detector technology, we can already today, or could before, make beautiful grayscale images of a certain quality and of a certain resolution, but that was not all. There were innovations around the corner. And the innovation was the disruptive technology of photon counting detectors. What is different here is that the X-rays after the patient, they impinge on a semiconductor, which is a direct converting material, and that means the X-ray photons are directly converted into electric charges. And we can collect these electric charges directly and individually measure each individual photon. And this is wonderful because this, the first time, gives us access to the color of the X-rays, something that is on a detector-based technology not possible with the established detector technology. And there are even more advantages of this photon counting detector technology. Because it's a direct converter and the pixel size is defined by the electric field, we can make much smaller pixels, detector pixels, than with a standard technology. We also eliminate electronics noise, which means we're only left with the Poissonian statistics of the X-ray interaction, which is good, so it's a very clean detector signal, and we weigh up low energy photons, which are very important for the tiny subtle contrasts in the human body. And this gives great dose reduction potential for the patients.
Okay, so now it's time to explain how does CT works.
Yeah, thank you so much for this question. I mentioned CT without saying what CT is. Yeah. CT is a primary diagnostic touchpoint. It plays a central role in medical imaging. It can be used to support interventions, and it's frequently used to follow up patients after their treatment. In CT, and we look into the interior of CT in a second, we bring the patient on a table into a bore of a rotating X-ray source and a detector, and we feed the patient through so we get morphological imaging within a few seconds, sometimes fractions of a second. And we also get functional information about how the body works, what are the processes inside the body by spectral X-ray techniques. Looking a bit deeper into the CT gantry, we see on top the X-ray source. That's an X-ray tube typically. We filter the spectrum. We have the patient. Underneath there's an X-ray detector. And in the middle you see a typical classical CT detector. You would not see the difference of the new technology on this scale in this image, but this is actually the core of the CT technology, and this is where the innovation went into that we call photon counting CT and that we realized.
Now, I just said that you are Vice President for Innovation, and I'm sure you're constantly innovating in your work. What's next? What's the newest in this field?
The newest in this field is, like I just said, we brought this detector technology into prototypes first, and eventually also in a product. And this, what you see here, is the Iotom Alpha. This is a scanner which carries 2 X-ray tubes at 90 degrees and 2 detectors. And they are rotating around the patients up to 4 times per second, allowing spectral information to be recorded, high resolution in space, but also temporal resolution of only 60 milliseconds.
The images we see are really stunning. Is this really happening now? Is this commercially available already?
This is happening now. It already happened, so it can be purchased. So this system is out in the market, and people are doing research with these systems. So we bring a new technology into the market, and what happens is research again. I would like to take you on a journey, a little bit deep dive in a few examples that I have collected with you. So first of all, the system has a high temporal resolution, which means you can make CT images of the beating heart. And on your left-hand side, you see the CT image of a heart for assessment of the coronary arteries and to see if there is any stenosis in one of the coronary arteries. And the new technology makes this much more quantitative and much more standardized for care. On the right-hand side, you see an example from pulmonology, where the spectral techniques can be used in order to measure pool blood volume, but also the inspiration and the ventilation properties of the lungs.
So the dynamic process is happening
The dynamic process is
happening
as they are happening,
right.
Exactly. What you also can do with a high resolution capability, you see on your right-hand side, musculoskeletal imaging, MSK imaging for the follow-up of surgical interventions. Yeah? And you see here pictures of patients who got their surgery already, and this is used for follow-up to see if these patients are really getting better. The same is true for brain imaging, which profits from the higher intrinsic contrast of this detector technology, which you can use again in order to assess the health of the human brain. This is not restricted, yeah, so the researchers, the clinical researchers now really explore in many, many clinical fields the potential of this new technology, and we are seeing lots of publications in the field, more than 350 with our prototypes and systems alone, and also other vendors are working on this technology, so there's even more publications out in the market. And I think we are closing a certain circle here. Paola.
Yes, we conclude with one more example of this virtuous circle that comes back from research in particle physics to industry and then to research in another field. Thank you very much, Stefan Kapler. Thank you. We are concluding with you this session on the world of particle detectors and moving very fast and furious to the third set of instruments that particle physicists need, that is computing, to the world of to the quantum world. And to do this, we start with a little teaser.
CERN is one of the most demanding computing environments in the research world. The sheer volume of data generated from its experiments is staggering. Particles collide in the Large Hadron Collider's detectors approximately 1 billion times each second, in turn generating a petabyte of collision data each second. With each terabyte, petabyte and beyond comes an opportunity for discovery. To harness this torrent of information, CERN has since its beginnings been at the forefront of innovation to meet the ever-increasing storage and processing requirements of a large community of scientists at speeds unimaginable just a few years ago. The World Wide Web was originally conceived and developed at CERN to meet the demand for automated information sharing between scientists in universities and institutes around the world, giving them near real-time access to data. Today, the worldwide LHC computing grid links up to around 170 computing centers in more than 40 countries to provide global computing resources to store, distribute and analyze the around about 200 petabytes of data expected every year of operations from the LHC. The laboratory's demanding needs encompass software development, data processing and storage, networks, support for the experimental program, and automation and controls, as well as services for the accelerator complex and for the whole laboratory and its users. CERN's expertise in machine learning and AI techniques also has the potential to address complex problems, such as environmental monitoring across large areas, understanding and mitigating the impact of air pollution, developing self-driving vehicles, and supporting doctors in making fast and accurate clinical decisions. Meanwhile, quantum entanglement, a physics phenomenon whereby particles can remain entangled even when they're vast distances away, is changing the future of secure identity management and cryptography to keep information secure 10 or 20 years from now. At CERN, processing meets visualization, and discovery knows no bounds. Our journey continues fueled by curiosity, powered by technology, and driven by the quest for understanding.
So the first speaker in this session, that is about the third area in which CERN has pushed technology to the limits, is Michele Grossi. Michele is a high-energy physicist specializing in quantum learning models, previously at IBM, now at CERN in the Quantum Technology Initiative as a quantum algorithm coordinator. So Michele, we've seen physicists need accelerators, detectors, particle physicists, but computing is also a very big area in which technologies have been pushed to the limit.
Yes.
Why is that?
Thank you. Thank you for the introduction. Good evening. So yeah, computing is really fundamental. Of course, I'm biased by that, but let's say that if we go to the slide, I want just to show you where is the challenge. We are talking about challenge in every field, in every context here at CERN. So I just want to focus on these big bubbles. So these big bubbles represent the amount of data that are stream generated or stored in different conditions. The biggest one on the top right is the data that are generated somehow at CERN. As you can see, this is extremely huge. It is more than comparable to the amount of data that are streamed or experienced by the well-known commercial companies like Google, Amazon, and so on. What does it mean? That means that it's not just a matter of the quantity of data, but maybe it's written here, it's hypothetical. Hypothetical because the technology challenge is there. Actually, we cannot store all the data we are generating. And so the role of computing at every level, from the hardware to software and algorithm, it's really to try to help us to collect as much as possible information. And so what is the role of quantum computing here? Our hope is try to see if this technology, in particular within the second quantum revolution, can help us to address this kind of problem, either from the hardware or from the algorithmic perspective.
So you mentioned the word quantum is a very important word here today. Yes. Before diving into the futuristic applications that you're working on and that are unfolding with the second quantum revolution, it is important to highlight here, especially for the focus we said of knowledge-driven research, how this quantum revolution was triggered. It was triggered by a formula written on a blackboard here at CERN by this man, John Bell, so a very theoretical scientific theory that for the first time proved Einstein wrong. It's the Bell inequalities theorem, and this generated the quantum revolution we are living today. And to explain how this happened, we have here today with us, unfortunately only on Zoom, three very elite scientists. I would like to greet, first of all, Professor Alain Aspect of the Institut Optique de Paris-Saclay and Nobel Prize for Physics 2022, who owes his Nobel to the Bell inequality theorem. Welcome, Professor Aspect, and really sorry for the delay. We have so many speakers tonight, so we are coming very, very soon to you. I would also like to welcome, in the middle of the screen, Professor Nicolas Gisin, who is Professor Emeritus at the University of Geneva and at the Constructor University of Switzerland, who is connecting from the mountains not far from here. And last but not least, Reinhold Bertlmann. Reinhold is connecting from Vienna and is a very close friend and colleague of John Bell. So we would like to start slowly with something easier to understand than the quantum world itself, with John Bell himself, because Professor Bertlmann, you knew him very well, and you had the first encounter, these are your drawings, with him here at CERN. You are muted? Okay, so now we are hearing.
Can you hear me?
Yes, very well.
Okay, so I met John Bell first at CERN. It was in April 1978 when I arrived as an Austrian fellow in order to do research in particle physics there. And in one of the first weeks there was a welcome party, and in this welcome party I met John. He approached me and asked me, what are you working on? I played quartonium. And this was already very interesting for him, so that he suggested to prolong our discussion in his office. And in his office, we already did some little calculations on the blackboard, and this was the starting point of our, say, wonderful collaboration and friendship until, from this time until his death.
Thank you for sharing with us your magic moments with John Bell. I go a bit quickly through your slides. You told us that John Bell, who is known as a theorist, was also an experimentalist in a way. He also contributed to particle physics and also to accelerator physics.
Yes, John Bell had, so to say, many friends at CERN. He was a very appreciated, and a very renowned physicist. For instance, he had close discussions with Tini Feldman. They worked on the W and the Z boson, which were discovered at CERN. Rubia and Van der Meer got the Nobel Prize for it. By the way, also Feldman got the Nobel Prize, but in a different field, in renovation of quantum field theory. And he also collaborated with Steinberger. And with Steinberger, he did the work on strange parmesons. And John started as an accelerator physicist. Yeah? He came to Harvard, to the Atomic Energy Research Establishment in, I think, 1949. And he did calculations for stabilizing the beams in these accelerators. There, by the way, he also met his wife, Mary. And on the right side, you see an accelerator, this accelerator of CERN. Yeah,
it's the Lear, yes.
Lear, yeah, it is the low-energy antiproton ring. And John collaborated with Mary, and they also have written a paper how to stabilize these antiprotons in the ring by a method called electron cooling.
I'll ask you just a last anecdote. John Bell wrote a paper on you at some point.
Oh, yes, yes. Now comes the great surprise and the excitement for me. It was in 1980 when I was back for a visit in my home institute. A colleague of mine rushed into my office, waving a preprint in his hand, and shouted, "Reinhold, look what I have found." I looked. What he had was this sock paper in his hand. I suddenly became terribly excited, and seeing the cartoon which was showing me, I must say my heart stood still. And the surprise was that John never mentioned a word about noticing my socks, about wearing my socks of different colors. This was a habit I had since my early student days.
Were you really wearing different color socks working at CERN at the time? Were you really wearing colors of socks of different colors?
Of course. I think since 1968, it was, so to say, the student revolution. This was my silent part of the student revolution.
But
and I did this. And John noticed this, yeah, but I did not notice that he noticed that, and he made some thoughts about it, because in this article he described the EPR paradox, the Einstein-Podolsky-Rosen paradox, with help of my socks, and he also derived the Bell inequality with my socks.
Thank you very much
So you can imagine this article pushed me instantaneously in the quantum debate.
Right.
And it really changed my life, you see.
And this is a very nice bridge to the quantum debate we are going to start right now. Thank you very much. Reinhold Bertlmann, thank you for connecting with us from Vienna. So, yes, we can start a quantum debate on the color of socks, and we can start with Professor Gisin, who, in Alain Aspect's word, is one of the key players of the quantum revolution, and is somebody who fell in love with Bell theorem. Let's look at the theorem again. No, it's not there. Okay, no, just let's get started on the theorem. This is a very difficult thing to explain to non-experts, but I think with you we can try.
Yeah, we start from the first revolution.
Yes.
So should I now talk? Or?
Yes, it's to you now.
Okay. So thank you very much. So I'm indeed in the mountains at Les Diablerets in a meeting actually celebrating 60 years of Bell inequalities with 30 colleagues, experts in the field, and 30 students. So here you see Einstein on the left and Bohr, and they had this famous debate and all that. And somehow one could say Bohr was correct. However, I should also like to say that it is really Einstein questions that really helped to trigger all this quantum revolution, the second quantum revolution, and all of today's quantum technologies. So sometimes asking questions, provocative questions, even if maybe kind of wrong, might be more productive than merely being correct.
So what are the fundamentals of this quantum debate?
Yes, so on the left, so here sketch, you have the classical world where things are always just fixed and well-defined. And on the right-hand side, you have the quantum world, the micro world. You know, I'm an explorer of the world of atoms and photons being particles of light. And these have some indeterminacy, intrinsic indeterminacy, that is going to lead to randomness. And we come back to that later. But maybe on the next slide, we can try to, here is John Bell, of course, and here you have a sketch of his experiment, but here I can try to explain. So you have what is really magical and so fascinating here. Why did I and Alain Aspect and many just fall in love at first sight when we read John Bell's paper, is that it completely shakes the intuitive idea we have of space. You can imagine now these two objects, far left and far right. Okay, we call it here Alice and Bob, and you have to imagine that they are really kilometers away. And the magical fact is that if you touch one of them, the other one shivers. And this sounds completely impossible. How could you touch one and the other one shivers? But this is actually really quantum entanglement, quantum non-locality, and these kind of things. You don't really touch them with your hands, you touch it with a measuring apparatus, and they react in a random way, in such a way that you cannot use this kind of non-local causation to signal. Let's just explain a little bit of all that. So at the beginning, you share some physical stuff between left and right, so between Alice and Bob, you share that. And then you perform measurements. These measurements are here indicated by this X that can take two values, 0 and 1 on Alice and Y on Bob. But the locality assumption is Bell locality, which is indicated here on the top left, is the very basic idea that what happens on Alice depends only on the local stuff, on the measuring setting and on the shared physical state, and not at all on Bob. And of course, vice versa, what happens on Bob does not depend on Alice. And if you make this assumption, which is a supernatural assumption, then you end up with these famous Bell inequalities. And the experiments, we'll come back to later to Alain. Yeah, this experiment, which is sketched here, but which was then realized, among other, by Alain Aspect, really proves that this inequality that you see even here with this small or equal to 2 that you see on this blackboard can be violated, not only according to quantum predictions, but even more impressively by real experimental data that have by now been realized in many, many places all around the world.
Yes, and the first person to perform this experiment was Alain Aspect. Alain Aspect, who got the Nobel Prize for proving Einstein wrong, which is the dream of all physicists. And it closed once and for all this Einstein-Bohr debate and proving that reality is really counterintuitive. So, Professor Aspect, I come to you now. Testing these inequalities was a very big challenge. We see here the laboratory. This is a photo, courtesy of Professor Gisin, of your lab, where you proved this experiment that John Bell designed. It was a big challenge. Not many people believed that it could be done. What made you decide to embark on such a daring adventure?
Well, it's exactly the same reason as Nicolas. When I read the short and fantastic paper by John Bell, it was, as Nicolas said, love at first sight and coup de foudre. I read that and I say, this is the most interesting problem I have ever found. I want to work on that. When I read that paper, in fact, there was already 2 experiments, one in Berkeley, the one of Clauser and Friedman, and one in Harvard. And they had contradictory results, but I knew that it took me a lot of time to build an experiment, so I knew that I would not be the one who would settle the debate or the contradictory results between Friedman, Clauser, and Holt and Pipkin. But I read at the end of the paper of Bell a short paragraph saying that what would be fantastic would be to change the setting of the measuring apparatus while the particles are in flight. And this had not been done by Clauser or by Pipkin and Holt. And I thought that maybe I should try to do that. And so, in fact, it was the idea of the experiment. I had, yes, this is what you see here. So at the middle, you have a source. One photon goes to the left, one photon goes to the right. And you want to change the setting of the instruments, and the instrument is quite heavy, so you are not going to change the instrument or to rotate the instrument in a few nanoseconds. So the trick that I found was building a kind of switch able to send the particle, the photon, either towards one instrument or towards the other one. And my setting was fast enough to do that at the very last moment after the particle leaves the source and in between, in the trajectory between the source and the detection. So this was the experiment I did.
And this experiment with its result earned you a Nobel Prize for Physics in 2022 with Clauser and Zeilinger. In the Nobel motivation, it's incredible how you put together on one side a very abstract theory, and on the other side, the fact that this theory opened the quantum revolution. This shows the importance of new knowledge in the most extreme way, something very theoretical that triggers a quantum revolution. And you said that Professor Gisin is one of the key players of the quantum revolution. So before coming with the last question to you, I want to ask Professor Gisin, why did you deserve this title of key player of this revolution?
Well, you should ask Alain. But I guess the answer that Alain would, I'm sure, agree, is really that, you know, here, before we were in a lab, and this was a kind of curiosity lab, people didn't really pay too much attention. I mean, that was really the dark times for quantum correlations. And then we opened it and went outside the lab and used the standard commercial telecom fibers, the standard fibers that we are using presently, for instance. And with these ones, and also with single photon detectors adapted to these optical fibers and the wavelengths, we could really go outside the lab, go to kilometers, more than 10 kilometers on this example. And then, of course, you open possibilities for quantum communications. Alain, you agree?
Oh, yes. As I told you several times, what impressed me is that not only you were a very good theorist, but you can go to real engineering, because people who look at that may not appreciate how difficult it was to go from the ideal laboratory situation to go to a commercial network of optical fiber. Of course, in Switzerland, everything is almost perfect, but anyway, playing with entangled photon on a commercial network was really a fantastic achievement. This is why I keep saying that you are the master of implementing this.
And actually, in this photo, we see that you received a very important visit in your lab, Professor Gisin.
Yes, indeed. This is a nice historical picture with the young guys who were doing this experiment at that time together with me. And in the middle, the lady, that's Maribel, who did pay us a visit while we were in the Swisscom Center on the ground playing with these fibers and entanglement.
So you not only did this experiment, but you also created a company that develops real products based on these new possibilities open by the characteristic of Bell non-locality, entanglement, and so forth. Let's go through a few of these technologies that are real things that are actually happening nowadays.
Yeah, absolutely. They are really commercial. And here you see only two boxes. So essentially, one of the basic idea was to say, let's put the source into one of the two boxes. Let's say at the source side, we call it Alice. And then you just have a single photon going from Alice to Bob. And inside, you have all these small boxes. You have all the hardware that is needed and the computer to change the settings and to analyze the data and to produce the fibers, the photons, sorry, and also to detect them. So here you have just picture of boxes that look very standard, but actually they are really quantum magical boxes in some sense.
And what do they do?
They exchange these photons, they achieve these correlations that Einstein didn't believe in, and these correlations, they have this remarkable property that they are actually cryptographic keys. So actually you have this very, very high, essentially 100% correlation. And at the same time, there is no possibility for an adversary to intercept these photons, because any interception or intervention would immediately destroy the correlation, reduce the correlation, and that will be noticed. So here we distribute somehow quantum correlation. We check that the correlation have not been disturbed, and then we can conclude there is no adversary, there is no eavesdropper on the line.
So it's super safe.
It is absolutely safe. And here you have examples of, okay, on the left side, you have a small network, Geneva, Lausanne, Lyon, on the Lake Geneva. In the center here, Poland, that probably today holds the largest quantum network in Europe, close to 2,000 kilometers. It's very impressive. South Korea has also a network which is maybe the most complex one. It doesn't show up here that it's so complex, but it's a very advanced one. And just, okay, there are more examples that are not here, but on the right-hand side, you see also the ambition of Europe to establish a quantum communication infrastructure really at this continental scale. So this is presently under development and ongoing. And here you have another example, which is a beautiful one in my opinion. So on the left, you see just the basic idea of a quantum random number generator. So you have this train of single photons that come on this beam splitter. And behind the beam splitter, you have two detectors. Let's say the red one, which is labeled 0, the blue one, which is labeled 1. I mean, they're identical detectors, but just labeled differently. And then you get, each time you get one click, you get a 0 or 1. And this string of bits is really perfectly random. So that's the principle, and then we were able to put it in this central little box, this 4-centimeter box, where you see ID Quantique, the name of the company. And then engineers are able to go even way further. On the right-hand side, you see now this millimeter-size chip, which is really very small and also low consumption. And this one is presently included in some of the Samsung phone, iPhones, or the smartphones. Not iPhone, sorry, it's a Samsung phone, never mind. And so this, they call it now this quantum galaxy. What it does is really have a source, a quantum source of randomness, and they use it in many banking applications, for instance. And so here it's probably the first mass application of quantum technologies. Here's another application which is very surprising. It's completely different somehow. So here you see the future space rocket, European space rocket, Ariane 6, which will be launched in a few months now, which will be the first rocket where the cables are not electric cables, but fiber optical cables. So all the communication, everything will be done like that, including triggering the engine. To trigger an engine, you will have a bright laser pulse that via optical fibers goes onto some matter that heats and triggers the motors on, the different engines on.
Can we trust that?
Exactly. So can you trust it? So before pressing the launch button, of course, you have to test all these optical fibers. Are they all correct, the same length, the correct length, and all that? And the usual way of doing that is to send a bright pulse through this optical fiber and analyze what comes back. But of course, if you do that now, you're triggering the engine on. So you cannot test it. So the idea, which is not a super idea, but let's send a very weak laser pulse in and still analyze what comes back. But what will come back is super, super weak signal. And there you need single photon detectors. So this is an application of single photon detection.
Which is dear to the heart of Professor Gisin, I understand, because he was one of your pupils, Professor Aspect, sorry, that was developing this technique long time ago.
Yes, it was Philippe Granger during he was my first PhD student, and we built the first single photon source, and we demonstrated indeed that when this photon goes on a beam splitter, it goes either on one side or on the other one, and because it is totally random, because of quantum randomness, then this is a perfect quantum number generator. And we also demonstrated that we can do things with extremely weak pulses. But once again, this has been put and developed and put to a wonderful level of technology by Nicolas Gisin and people working with it.
And when you were working on that, did you expect that it would end up to trigger and launch rockets?
Certainly not, but you know, when I was working on the test of Bell's inequality, I had no idea and no expectation that one day it would be useful for something. I thought I was settling a theoretical problem, a debate between Bohr and Einstein, and it was good enough for the young physicists that I was at that time. It has been a complete surprise. By the end of the 80s, for the first time, I heard of an application when Arthur Eckert, a young student at that time, came to me, sat in front of me at a table and said, "Do you know that with your entangled photon, one can do quantum cryptography?" I was absolutely amazed by that. And from that time, I have seen all this flourishing of quantum technologies. It's a wonderful surprise for me.
And this is the best description of how knowledge and innovation are so profoundly and unexpectedly linked to each other.
One point that I can make is you look at the time delay between a fundamental study and the real application. Typically, you find 20, 30, 40 years. And I have many examples of that. Of course, I have no time to say it, but I have many examples of that. And you know, in my case, it was in '82, and the first applications came, let's say, 20 years later.
Yes, and if you think of the Newton laws, you think how many years later they used to launch rocket. The same laws, it took more than 20 years.
Centuries.
So to know more about this fabulous quantum world, Professor Gisin has written a book that is called Quantum Chance and was prefaced by Alain Aspect. And of course, the book was written in French and not in English, so you can find it Quantum Chance or L'impensable hasard in French. And we really appreciate that you are sharing this very fresh knowledge with the wider public. These books are quite accessible, and it's really great. So I know that you are very much under pressure. We are late with the program. So instead of following the program as we had foreseen, so giving the floor to Michele now, I think we could go straight to. We will see these applications with Michele later.
Oh, I'm a realist.
Yes,
and,
to the voice of John Bell. Let's listen to the voice of John Bell.
It's a kind of, I think it's an artificial position which scientists fall into when they discuss the meaning of their subject and they find that they don't know what it means. I think that in actual daily practice, all scientists are realists. They believe the world is really there, that it is not a creation of their mind. They feel that there are things there to be discovered, not a world to be invented, but a world to be discovered. So I think that realism is a natural position for a scientist. And in this debate about the meaning of quantum mechanics, I do not know of any good arguments against realism.
It was the voice of John Bell, courtesy of, once more, Reinhold Bertlmann. Thank you, Reinhold, for sending us this recording, showing how these new findings are also triggering a philosophical debate on the nature of reality itself. And I just wanted to ask Alain Aspect, what do you think of this philosophical sort of derivation of these theories and of these discoveries? Do you agree with John Bell about the concept of reality? What are your thoughts?
Well, you know, this is not a scientific position. It's a philosophical position. But on this debate, I sit on the side of Einstein and Bell. That is to say, I am a realist. And then the price to pay is that I have to accept non-locality, because what the violation of Bell's inequality show is that you cannot keep with a model where you have both realism and locality. So I am a realist, like Bell, like Einstein, and I accept non-locality. I think that Nicola has the same opinion, and I think that Reinhold is on the opposite opinion. So it's interesting to see that we have different opinions.
Reinhold, will you tell us your last word on this?
Well, as Alain already said, I have a different opinion. I would say I'm not that realist you might think due to my socks. Yeah, I think that what exists is somehow, I would say, is somehow different. We see it. I like to compare it with what exists is like a continuous spectrum, and with our techniques, we only see the small lines. We only see many small lines, but we don't catch that what really is, so to say. Yeah. Yeah, it's difficult to say. I mean, I agree with Alain, it's a philosophical position. Yeah.
What I wanted to show with this...
It is important, we have to include, so to say, the instruments, all the senses we have in this picture of reality. Yeah, and as John said, I finished quickly. John said we are discovering the world. Yes, but I think we are also constructing our world. Yeah. Yes.
Okay, so I just wanted to make a little provocation on philosophy, just to show that a theory that is still bound to interpretation has already changed our world with the second quantum revolution, with all the technologies that Professor Gisin, for instance, described. And this is how it is. This is how the world functions. So I would like to thank you very much for being so patient and waiting all this time that we have accumulated a little bit of delay for us from Paris. Merci beaucoup, Professor Aspect. From Diableret, from the Swiss mountains during the 60th anniversary of Bell Inequalities celebration that you are organizing with the University of Geneva and the University of Vienna. And thank you, Professor Bertlmann.
And Constructor University.
And Constructor University. And thank you, Professor Bertlmann, for all the anecdotes and photos and drawings and everything you said about John Bell. Thank you very much. We say bye-bye to you.
Bye-bye.
Bye-bye.
Bye. And we continue here with Michele. Sorry, I really needed to give the floor to our elite scientists, first of all. And we can go back to your slides and to the describing how CERN is surfing the wave of this quantum revolution, that the second quantum revolution that is already happening, as we saw.
Yes, sure. It was really a great pleasure to hear directly from the scientists who contributed to this. I would like to tell you that due to this tremendous amount of technology development, in particular for quantum science, I will try to give you an overview about what CERN is doing, why there is a specific initiative called Quantum Technology Initiative. And I will try to be quick, but at the same time to show at least three main pillars of this initiative. Let's start with this beautiful representation. I took this illustration from the University of Rochester. And essentially what we see here is that we are able to manipulate quantum objects and really, I would say, play in this very counterintuitive world. And practically what we can do is that Here we can manipulate electron spin in silicon. That is to say that we can manipulate information at quantum level. And this is a sort of definition of what we can say about quantum sensing. So quantum sensing is really the opportunity to build objects that play in a quantum world, and then we are able to detect and measure physical quantities that we cannot even measure with classical sensor. We have seen before a beautiful picture about the sensor that we have here at LHC. And the idea is that this quantum sensor can be even more sensible to low energy signal. This is very interesting. At CERN specifically, we have a lot of knowledge, as we have heard so far. We are working on cryogenics, radio frequency, on superconductivity to detect the gravitational wave. We are working on building exotic ions and sensors to build, in particular, atom clocks and to measure particles beyond standard model. And atom clocks allows me to go to the second pillar, which is quantum communication. What I can say after Professor Giusan. You have heard about...
He's no longer there, no worries.
Yes. I mean, we understood that we can really exploit quantum mechanics to transmit information in a very secure way. But beyond that, we can say that already at CERN we implemented an end-to-end analysis with quantum key distribution, actually using the machine provided by that company. And beyond that, let's say that I took this picture to mention about the technology and a collaboration that was born here at CERN called White Rabbit. White Rabbit is technology that can work at nanosecond precision and picosecond accuracy for synchronization. The synchronization at that level for quantum detectors is fundamental. And the idea is that we want to implement this for a long range. And in particular, we want to distribute time and frequency to the experiment at CERN. As we heard, we need additional precision for the experiment. Not only that, and this will connect to the last topic, which is computing, actually what I am working on, is the ability to use quantum communication to connect multiple computers together. And the idea is that we can really construct a distributed quantum structure and quantum infrastructure. So let's look at this beautiful object in the middle. This is a quantum computer, the superconducting quantum computer. We heard a lot about superconductivity. This actually works even at a lower temperature. It's 50 millikelvin. And the reason why we need to work at very low temperature is because this is where quantum mechanics exists and is not affected by external noise. And let's say that in terms of computation, this is an extraordinary moment because essentially we are in front of a very computing paradigm shift. And I want to say that for decades we've been, let me say, simplifying the description of the world with bits, which are just 0 and 1. And with this 0 and 1, we can build all of the experiment that we have CERN, the ability to collect all the data. However, with quantum computer, we have new computational paradigm. And usually people use a coin to describe what is the quantum version of a bit, which is a qubit. I don't have a coin, actually, but I will try to give you just a glimpse of the idea. So we said a bit are just 0 and 1. It's a deterministic calculation. The idea is that a single qubit can be thought as a sphere, or if you think of a coin, the operation of a qubit is like when you toss a coin, and eventually you have the possibility to have, at the same time, 0 and 1. But this happens only during the calculation, because we know that when we measure everything, then we collapse either on 0 and 1. And a qubit is a richer object in terms of information content, but the game changer comes when we use entanglement. So when we connect qubits together, and essentially we can think of a quantum algorithm as something that is cached there. So essentially you have different qubits, you can connect qubits, you can create entangled state, and here comes potentially the possibility to have an exponential amount of the information that you can store and you can manipulate. Of course, quantum computer will not solve everything, for sure. It's a completely different approach. We have some ideas about where this will be very useful. Of course, we are dealing with quantum field theory, so it seems that we are using an object that speaks the same language, which is good. And for other applications, we need to understand how to attack the problem in a different way. And now it's a very interesting technology. And now I want to go to my last slide. And I want really to close this loop of the virtuous circle of knowledge and innovation. I want to connect the dots. Why? Essentially, what we are seeing here in this beautiful picture is a representation, an illustration of the first ever observation of quarks entanglement at high energy. This is a picture taken from real data took from the experiment of Atlas. And this is really an amazing thing, and it's kind of fascinating because essentially it's true that all this kind of experiment has been built as a general purpose, one, but the ability to prove also this quantum mechanics law is incredible. And our calculation allow us to say that at some point in the future we'll able also to measure Bell inequalities here at CERN. So that's really fantastic.
Amazing. Thank you, Michele. Thank you for these last words. There is unfortunately no time for Q&A. We've been really going through accelerator, detectors, computing, the applications, the illustrations of how some very theoretical knowledge on a blackboard at CERN is now changing our world and will still continue to change it because, as you said, the potential for applications is enormous. So I would like to thank all the speakers from the first to the last, just in alphabetical order. Starting with, let's say, if I'm still fresh enough to remember, we started with Alessandra Lombardi with the accelerator presentation, Amalia Ballarino, Tabea Arndt. In the detector section, we thank very much Daniela Bortoletto for her incredible insight. Then I would like to thank Jan Jakubek and Stefan Kappler for the marvelous technology applications that they are deriving from particle detectors. Last but not least, we already thanked our three special guests from far away, in particular Professor Alain Aspect, Professor Gisin, and Professor Bertlmann. And thank you, Michele, for being patient.
It was a real pleasure. Thank you.
So, as is customary, at the end of each of these events devoted to the 70th anniversary of CERN, I would like to call on stage the mastermind behind all this, Luciano Musa. Big applause. And Anna Godinho, Head of Communications.
Good evening, everyone.
To tell us about...
I really hope you enjoyed this event. We really had the privilege to host experts on many different fields that with their unique insight, they have highlighted this connection between fundamental research and applications. Now you've seen that we had vivid examples of technologies which have been developed for particle physics, at least originally have been inspired by particle physics, have found immediate applications on different fields or everyday life. But also we have explored this more profound connection between theoretical and abstract concepts and transformative technologies which can have the potential to transform society. So I think these two narratives, they really carry a very powerful message. Maybe that is the take-home message for today, that whether it's an immediate return or it takes decades or centuries, fundamental research is really at the heart of human progress. And now, before closing the evening, I would like to thank again our distinguished speakers and all the people who have contributed their passion to bring the event to life. Now, I cannot list all of them because there are many people I would forget someone. But let me then mention especially Paola Catapano.
Thank you, it was a pleasure.
Who not only has moderated the event, but also together with Lynn Kreschmeyer, who is also here with us, have curated the preparation of the event. And I don't know if we have the program. Yes, behind me we have also the program. So let me conclude by inviting very warmly each of you to also participate in the other very interesting events that we have lined up for the year. So you see we have still 3 more gatherings awaiting us. So mark your calendars with the upcoming one, the CERN and Extraordinary Human Endeavor, on the 19th of May, and we really hope to see you numerous also at that event. And
can we reveal the big guest of that event?
Yes, we can. So we will have, well, we will be talking about the global partnership, openness in science, and we will do this with many distinguished guests, but in particular it will be our pleasure to host Tim Berners-Lee, the inventor of the World Wide Web. So we really hope that you will participate at this upcoming event. So, and with that, then thank you very much for being here tonight. We wish you a good night and a safe return home. And yeah, we look forward to see you again here.
Yeah, and a big thank to the wonderful technicians that are supporting us night and day with the preparation, and especially during the live. They're really fantastic. It's a great pleasure to work with all of you. Thank you very much.